Howdy, everyone. Starting a new topic today, topic 3, illumination of the workplace. This is where we're going to talk about light sources, how much light, what's the quality of light that you need to have a good visual context for the humans in your work system. So illumination, what are we looking for here? What's our design goal? We want proper illumination. That does not always just mean give me more light, though. So it's very particular. If we do have things properly illuminated, then the viewable objects are maximally viewable by human eyes. We have better contrast. We talked about how contrast is an important feature for vision, and being able to see the differences in the lights and the darks, the foregrounds and the backgrounds. We have less visual fatigue when things are well lit. Basically, our focal system of the essentially the lens is less fatigued by needing to change planes, depths of view, and to adapt to different lighting conditions when we're maximally visual. I already mentioned this, but proper illumination doesn't mean give me more light every time. You want the right kind of light. You want the light to come from the right direction, and you want illumination that is not necessarily going to hinder what you're using that illumination for. And so, a good example, which we'll talk about in this topic, is glare. Okay, so glare is a good example of adding light but not making what you're attempting to see more visible. Okay, so we'll also talk about reflective properties, because lights are not just coming from a energy applied light emitting source. It's also all around us. It's reflecting off of surfaces. Everything that our eyes can see comes from light that is reflected off of something else or emitted from something. All right. So the first, there's 4 subsections in this one. The first one, we're going to talk about the basics of photometry. I'm going to define a couple of key terms that you're going to need to know, right? And so here we go, illumination of the workplace. So here we are. Everything that's labeled here, I guess these 4 terms: luminous flux, luminous intensity, illuminance, and luminance. All of them have about 8 common letters. And so from a human factors standpoint, I say, well, what do I say here? So this is going to be a challenge to keep them straight. This is also why I want you to, have access to your notes and things when you take quizzes and exams, because I don't think it's proper for you to have to remember every letter in these 4 very similar terms, but you do need to know which is which and which goes with which concept. So luminous flux, this is the first one we'll define. I'm going to go over them really quickly here, and then we'll get into detail. Luminous flux is about the energy emitted from a light source. Okay, luminous flux is a property of that light source. Okay, so this is the sun, or this is a light bulb. Okay, that's light energy in all directions is what we call luminous flux. It's input energy, output light energy, right? Now, when we're talking about light that strikes something which is to be seen, now we're interested in light going in a certain direction. So this is probably the most confusing distinction, is between luminous flux, light energy emitted in all directions, and luminous intensity. That's the portion of this light energy that goes in all directions, but the portion of that energy which is going in the direction we're interested in, which is going in the direction that we're analyzing. Okay, so that luminous intensity of a certain, certain level of light energy reaches this object and strikes it. When the light strikes this object, it illuminates it. Okay, so illuminance is the property of how illuminated is the object I'm trying to see. All right, now light strikes this source. Some of it is absorbed, some of it is reflected off. The light that's reflected off, this is the light that's available for my my retina. Okay, so my eyes don't get any sort of visual experience unless light strikes the retina. And so then this light, which originated in the center of the sun, came all the way to Earth with a certain intensity. It struck this piece of paper on the ground. Some of the energy was absorbed, some was reflected off. This is the energy that your eyes can pick up. So it's different from the luminous intensity because it matters how much is absorbed versus how much is reflected. But this is the measure that we're ultimately talking about, the quantified energy that reaches the eye, that reaches the retina. Okay, so now these four terms, getting into more detail here, a little harder, a little deeper. Okay, so the first, again, luminous flux. Sometimes I'll say total luminous flux, because if I add an extra word, it sticks out a little bit more sometimes. But again, this is, think of it like this. I'm going to plug in a light bulb, and electrical energy, which is quantifiable, goes into that lighting unit. And some of that electrical energy is then transduced into electromagnetic radiation with the, if it's a filament element or if it's fluorescent gas, fluorescent neon gas tube. Then yes, so then it ignites and it emits energy in the form of light or heat or both, always both, I guess, but various amounts. But there's only as much energy coming out as what goes in. Okay, so this defines all of the energy that is in the electromagnetic radiation spectrum. Okay, which is all visible light, but also heat, right? Also heat. Think of like the predator and being able to see, heat sensitive vision. All right, so the other thing is this energy goes in all directions. Okay, the sun is a great source of illumination, for us here on Earth, but the vast majority of the sun's energy does not strike Earth, right? It goes in all directions. The sun isn't using a reflector to direct its light at the Earth. It goes in all directions. Okay, so only a fraction of that is available to come to Earth, for our visual experience. But so far we're talking about energy in all directions. This is a property of the source. It's also important to know that we usually assume a spherical light source, meaning that the light is emitted spherically in all directions with roughly equivalent density. In reality, that's not usually the case. And here's one example, is in illuminating a light element, there's probably an incandescent filament here, in this bulb. And there's light going in most directions. Actually, there is light going in all directions. It's just that some of it is obscured by this fixture. Okay, so if you want to think of that, that's sort of in a way wasted energy if we're trying to convert as much energy as we can into usable, visible light. So it's not really wasted, but I do want you to recognize that there is light energy that is going in all directions, being emitted in all directions, just like with the sun. It's just that, boom, it's kind of striking a plate there, and so the light is not escaping out of that into be accessible for the human eye. All right, erase that. Okay, very good. And stop the mouse back. All right, so spherical source maybe is partially obscured almost always, if you can think about, well, otherwise how are you applying electrical power to something unless you have an input. And then we also have light sources that don't, by their fundamental shape or by the way that they excite their fluorescing gas interior, sometimes these don't emit in all directions evenly. So LEDs are a good example. A lot of LEDs, based on the color of the hue, and then I suppose the physical properties of the bulb around it, but they tend to have characteristic sort of beam angles, right? And so we have to think about that too, because light, electrical energy going in, light emitted going out, it's not always considered perfectly spherical. So what I'm showing you here is just basically the real world. We're pretty much always going to assume a sphere when we talk about things like luminous flux and luminous intensity, which is the next. Yes. So we can have different beam angles, for different light emitting sources. Okay, now total luminous flux. We'll talk about the quantity of the energy in terms of this unit, the lumen, abbreviated LM. This is the SI unit. This involves meters. So, or I'm sorry, this is the same realm as meters. When we start talking about lumens and distances, then we'll usually go with meters. But we'll get to that here. All right, so that's luminous flux. That's number one. That's the sun. That's all. That's how far we've gotten so far. Next, the luminous intensity. Now we have a letter to go with this here. So we have a variable I. Now here's okay. So this is all right because intensity starts with an I. So I goes here. Just remember, we're talking about the intensity of the luminous energy, which also is talked about in terms of lumens. However, we have to specify the difference here. So we want to talk about, if we're talking about light from a source, and we wanted to distinguish, are we talking about all the energy being emitted in all directions? That's total luminous flux. Or are we talking about the energy emitted in this direction, which is, the sun pointed at Earth, the fraction of the light from the sun that reaches the Earth? Okay. And so we specify that in a three-dimensional angle called a steradian, a subtended solid angle. Looks like this. So if this is the sun, and if the Earth is over here, we want to know, well, how much of that subtended angle of energy strikes the Earth? Now, a steradian, you can see the root radian in there. And so it is an angular measure. It's a 3D angle, I guess, or a conical angle. And so just like when you talk about there's 2 pi radians in a circle, there are 4 pi steradians in a sphere. If you want me, I'm not going to do the mathematical proof for that, but you can find it online. I'm sure you can, so you can believe me and understand where that came from. It's a little confusing to me how we make this next step. Okay, so generally, you can imagine in a 2-dimensional space, we would say, well, how much energy per degree, per angle, right? And then that makes one single degree, in like a 360 or let's say 1 radian. That's a quantifiable amount, right? And so I get a little confused here because we start talking about energy per steradian, but generally we also say energy in any direction is in a steradian of direction. Okay, so here, what's a good one for this? Yeah, it's a little goofy. But so far, I hope so far so good. So the difference here, lumens in all directions, total luminous flux. Lumens in just the direction I'm interested in. That direction happens to be defined by this geometric term called a steradian, and there's 4 pi of them in a sphere. So this is interesting because if I know this number, and if I can assume that my light source is a sphere, then here is my conversion between the measures of luminous flux, total luminous flux, and luminous intensity. The difference in those two is a multiple of 4 pi, because I'm either talking about everything, divided by 4 pi, and that's 1 steradian, or if I multiply that 1 luminous intensity times 4 pi, it's a way to approximate the total energy in that source, the total luminous flux. Okay, so now here's our unit when we're talking about luminous flux. Now, I already mentioned the common word lumen here. All right, and now we have lumens in a direction, or lumens per steradian for this class. This is definitely as much as I'm going to try to say, because you can find slight different wordings, and they can. I've spent 11 years teaching on this, and I still get confused if I look at too many different sources. So I go with the most centered on this class source, and then I handle questions one at a time as we go. For this class, we are talking about lumens per steradian, abbreviated like this, lumens per steradian. And then we have a single term that we use, candela. Now, the reason this looks like the term candle is because it is literally, it's set, the unit is set. Lumens as an energy are basically measured according to a scale that started with somebody saying, if I hold a candle, at arm's length or whatever, and I look at it, how bright is that candle to my eye? They say we're going to call that one candela, or one candle power, you may also hear. But a candela is mathematically equivalent to a lumen, a single lumen, at a given direction, steradian. Okay. All right, so now I mentioned already there's this conversion factor of 4 pi. And so I just want to then bring in it full circle here. This will help you kind of see where we're coming from. If I have a 1 candela CD, 1 candela, yes, okay. Oh, I'm sorry, I get it now. Okay, so if I'm asking of something that I measure as having a 1 candela luminous intensity, right? Because 1 candela goes with luminous intensity, right? Candela right there. What is the total luminous flux? The conversion factor here is, again, 4 pi, because I've got 1 lumen in 1 steradian if I'm looking at it. And if this is a little miniature star and I can put my arms, my hands completely around it, and I'm asking the question of how much light energy strikes my hand somewhere, that's the light in all directions. That is the total luminous flux, and that is a factor of 4 pi. All right. Okay. All right, so our next term in following our little graphic here in the top corner, we have luminous flux, total energy, luminous energy, or luminous intensity, the light energy in one direction. And now how do we categorize how much light energy strikes an object that we are trying to look at? And we generally quantify this energy by the surface area over which this energy is acting. So if you can think about a really bright light, it's also spreading its energy as it moves across a two-dimensional surface like this, right? So the illuminance, okay, so illuminance starts with an I. Don't be confused, because luminous intensity, while it actually starts with an L for luminous, it is used, I is used as the abbreviation, not for illuminance. Now for illuminance, which starts with an I, we use E as its representation, right? I lost my sound effects, hang on. Be right back. Sorry. Bring. There you go. So don't forget that E, confusing, stands for illuminance. The physical units of illuminance are foot candles. Okay, so we already talked about candles in candela, which is, you know, the approximately the luminous intensity of a single lit candle. And now how much light goes from that candle onto something that you're trying to see. Now it depends on the energy emitted from the source in a direction and how much of that surface is being struck by that amount of luminous intensity energy. So a foot candle is basically what we represent as holding a candle about a foot away, and the amount of light that is striking an object about a foot away is a foot candle. Mathematically, these are represented as lumens per foot squared if it's a foot candle, okay, or lumens per meter squared if it's lux. Okay, I think I maybe misspoke a little earlier when I said most of the time we're specifying these units with meters. Lumens go with either English or SI units or you know, British units, I guess. So we can talk about the amount of energy that strikes a square foot, that's a foot candle, or the amount of energy that strikes a square meter. Because a square meter is larger, generally we talk about there's more, it takes a greater amount of energy to, let me think. Here's our conversion, right? So if you have 1 foot candle, you actually have 10.76 lux, because if you were to take that same amount of density of light and spread it over, have that same density over a square meter, it would be 10.76 times as much. So there's your conversions back and forth. It's entirely about the conversion between square foot area and square meter. All right, so this depends on several factors, okay? So some of this is intuitive. I want you to think about what makes something get brighter in relation to where there's a light source. So the luminous intensity matters. If I add more energy to this system and there's a larger luminous flux, then also I have a larger luminous intensity. So if there's more energy in all directions, there's more energy in each individual direction. So that would make our illuminance go up. And again, that's about the lumens, the energy that are getting there. The object surface area, if it changes surface area. And this is the one where we're really going to play with it, is the distance. And I've made a little animation here to help kind of recognize why we sort of interchange these, the distance from the light source and the square area over which the light is acting. And so got a few demonstrations here. So here we have, an object on a desk that we're trying to illuminate with a light. We can increase the amount of light energy. So we turn up the power, that would make it brighter, right? So total luminous flux goes up, then that means luminous intensity goes up with a, it's a direct, remember the difference between luminous flux and luminous intensity is a factor of 4 pi, right? 4 pi, that's a good one to remember. And then the illuminance will go up by that factor as well. So if you don't change anything else about the location of the lamp, and you only change the amount of energy going into that light system, therefore more light energy coming out, then all of these factors affect illuminance, how much light energy strikes this paper right here. All right. We may also say, hey, here's a light bulb. And you remember I made the point that the bulb emits light in in all directions. We approximate that as a sphere, as it's emanating in a sphere. Then there's a lot of that energy that is not pointed at the thing we're trying to see, and so is effectively lost. It's effectively not usable for illumination. Now, if we redirect some of that light by using a reflector like this, and this is something called a parabolic reflector. We're going to talk about that in the 4th subtopic here, a parabolic reflector. This effectively takes whatever is the luminous flux energy, and it's no longer just whatever is unabated being, emitted in this steradian direction. We also get all the light up here, and we can kind of redirect it and refocus it, and we get an effective, denser amount of light beams going in that same direction. So that's another one we can do. Or we can close the distance between the light source and the object, right? So I move that light closer to the table, it will effectively have more illumination on the table. All right. And one way to think about this is we're increasing the number of steradians of emitted light that are now contacting this surface when we get closer with that object. So I'll show you how that kind of works here in this illustration. So here we have energy in all directions, total luminous flux. We've got whatever's going on that table, and we want it to be illuminated. So if you want to like sort of a proxy here, you can kind of look at, oh, well, we've got about 3 beams of light that are striking this. There's, infinitesimal distance between beams of light. Just, I think conceptually, if you think about roughly, there's this much energy striking and all the other energy is going elsewhere. Okay, now, if I use this parabolic reflector, I put that over the surface. Now all of that light energy is directed in a constrained space. So the light that was going up here, now it's redirected down here. Oops. Now it's redirected down here. So now it's like there's twice as many beams striking. So that effectively makes the surface more illuminated as well. All right, now here is the big move. Ready? So get ready. We're going to move closer to the table and watch how more beams of light strike the table when it gets closer. Okay, there we go. So we get real close and it's going to be much more illumination. So those three things can be, manipulated to change the effective illumination of the surface you're trying to see. This is a photometer. I'm at my house right now and I'm going to campus tomorrow, and I have a photometer at campus. So I hope I remember to get it. And then in my next video, or I can do another demo, I can show what sorts of values we get around this space, for example. One of the interesting things I always like to point out is, remember how we talked about the adaptability of the retina and how it's so incredibly much brighter in outside than it is in most indoor environments, but our eyes adjust to it. We don't really notice a huge difference. So a photometer is always an interesting thing to use, because we may have something like, like 1,000 lumens if I hold it up to the or thousands of 1,000 times more lumens, let's say, if I'm outside. It can be 100,000 lumens, for example, maybe, and it's much less inside. So we'll see what it is when I remember to get that thing. But this is a photometer measures illuminance. Now you may say, well, why doesn't it measure some of the other things? It's because light has to strike a surface in order for any sort of sensing to happen here. And so if we're talking about light striking a surface, how much energy strikes it, that is, the surface now is the photometer sensing pad here. Okay, so this is going to give us foot candles or lux. Again, remember those, the 2 units we're going to get from a photometer. Foot candles I'll probably stick with for now, but realize again, lux might be a more common term in the general scheme of photometry. But yes, they're convertible. They can be converted back and forth. All right, good. So yep, there you go. There's your photometer. It measures illuminance, which is abbreviated with an E, not an I. All right, typical lighting values. Good. So by its namesake, a candle is roughly 1 candela of luminous intensity. So wherever you view it from you're getting that much, 1 lumen per steradian is reaching your eye. A lighthouse is 100,000 candela. Okay, so wow, that's 100,000 candles is how they would, approximate the power of a lighthouse. If you have an incandescent light bulb, that's almost no longer the norm anymore. We have all kinds of different technologies, LEDs, fluorescent, compact fluorescence. But your traditional metal wire, metal filament, and if it's a 100-watt bulb, it emits about 100 candela. Illumination, right? So E, there it is, there it again, one more time. Starts with an I. It's abbreviated by E. The illuminance, I should say, and illumination are they're not synonyms, but they have the same root. We're talking about the same general property here. How much light is striking this object? So moonlight. How much light does it? You can think of this like I'm holding up a piece of paper and I'm trying to read this in the moonlight. So I guess we've switched units now. 0.1 lux. 100 times greater is street lighting. So go from no street lights on to street lights on. It's 100 times more luminous. Office lighting about 300 lux. So maybe we'd call that about here. I'll test it with my photometer. Again, remember, these are lumens per meter squared that I'm showing here. So maybe it is a little bit of a brain exercise to not get these two mixed up. But lux and foot candles, that's like the SI and the British units here. Now outside, 1,000 lux. Okay, 1,000 just with the clouds out, and now direct sunlight. That's where I got the 100,000 from. So if you stare directly into the sun, that is a huge amount of light energy striking the surface of your retina. And we can talk about illumination of things we're trying to see, or illumination of the retina itself. It's all about light energy striking a surface, and that's what we're measuring. And if light energy strikes the surface of your retina, it will allow you to have a visual experience, but it also can be damaging if it's extremely, strong light. That's why you should not stare into the sun. All right. Okay. So 3 of those terms we've gotten through so far. Luminous flux, total luminous flux. It's energy in all directions. Luminous intensity. That's the energy, but in one particular direction. Illuminance is how much of that light energy strikes an object I'm interested in. And now we have one more term, but let's get, I guess we've already defined this guy here, illuminance, foot candles or lux. Don't forget those two could be used. They can be converted back and forth. All right, so some light is absorbed by this object, some is reflected off. The light that is reflected off, this is where we start talking about, okay, now we've got the light energy that represents the beam of light that is the imagery that the human eye needs to be able to process. So this is the light that is bouncing off of the piece of paper you have that is reaching the retina that is causing the visual experience. So I don't want to get these two things confused because I could be talking illuminance of the retina. And that's a question of how much light energy reaches the surface of the retina. That's not the same thing as me saying how much light energy is available for me to read something. It's usually used for more things like is this going to cause damage if I shine that much light into the retina? Okay, and it's got to be light from a source. So typically it's not reflected off of something, although I'm looking at a luminous display right now that is emitting light directly into my retinas. And so you can talk about the luminance of this emitting surface as well as the illuminance of when that light strikes the surface in the back of my eye, the retina. Okay, so I've been really drilling on these 4 terms. They are difficult to distinguish. You may want to go through this a couple times until you're pretty comfortable with it. But finally, we have something that makes sense because luminance, our last link in this chain, in this process of light getting to our eye, is abbreviated with an L. So at least that much makes sense, right? And so then this is, I have the amount of energy reflected off the object's surface. It could also be transmitted through. So literally right now, as I look at this screen in front of me, the luminance is the light is transmitted through a mostly transparent protective surface, right? So however much light is available for the eye, that's a great way to think of luminance. It's whatever is not absorbed by the object or the intervening medium. All right, and we close on just one more review of these 4 terms. So luminous flux, total energy, light energy being emitted in all directions. A portion of that energy is what we're interested in because it's what goes in a certain steradian direction. And so that's the luminous intensity. Luminous flux specified in lumens as units. Luminous intensity specified in lumens per steradian, also known as candela. Candela, that's the term we're going to use, remember, in this class. Mathematically equivalent to lumens per steradian, okay? Now those lumens per steradian strike a surface, and then that surface has properties of its surface area. And so if you're interested in looking at the entire surface area, you're interested in how many beams of light strike that surface. That's the illuminance. That's abbreviated with an E. And that represents, again, how much light is striking the object. Some of that light is absorbed, some is reflected off and available for our retinas, right? And then that's the luminance. All right, thanks. I know this was a lot of repetition, but I hope that it helps get these 4 terms straight.